Okay, today we are going to talk about this compressibility chart. We won't go too far in today because we have an exam going on next week. So I will only talk about compressibility chart and moving boundary work, which is right after this one. So let's talk about this compressibility factor. So we learned ideal gas equation last week. So PV is RT. Last week? No, last Tuesday. So we can use this ideal gas equation whenever gases behave like an ideal gas. Then when a gas behaves like an ideal gas, when it has low density. So when a gas has a low density, when temperature is high or pressure is low, then what about if your system is under low temperature or high pressure? Is there any way to use this ideal gas equation? Yes, there is. We can use compressibility factor Z. So we can modify this ideal gas equation by this way. PV is Z compressibility factor times RT. It's not a complete solution, but it can decrease the error of this ideal gas equation dramatically, so we can, predict some of the properties in this equation. So we are going to study how to determine this Z, which is very simple. We are going to use compressibility chart. Looks like this one. It looks complicated, but it is not. This horizontal axis is reduced pressure, P of R. So this one is P of R, reduced pressure. By the way, this reduced pressure can be determined by the actual pressure of your system divided by critical pressure. And each line represents T of R, reduced temperature. And this reduced temperature can be determined by the actual temperature of the system divided by critical temperature of the system. So to determine if you know T of R and P of R, you can find a compressibility factor Z, which is this vertical axis. Then to determine this P of R and the T of R, we need to know critical temperature and critical pressure. Where can we find these two properties? From table A1. So if you go to table A1, you can find these critical properties. And here is table A1. 1, 2, 3, 4. This one. This is critical temperature. And this is critical pressure. So based on the system you have, you can find T, critical temperature, critical pressure, and determine reduced pressure, reduced temperature. Then you can use the compressibility chart, which is pretty simple. So that's everything. Let's solve one problem together to learn, how to determine this compressibility factor, and then, the evaluate a property. So we have superheated water vapor for our system, and we are going to evaluate the specific volume of this superheated vapor by using three different methods. The first one is the ideal gas equation. As we already know, you cannot use the ideal gas equation for water, but let's just try it. Of course, this, the value that predicted by this ideal gas equation may have a significant error. Then we are going to use the compressibility chart to minimize that error. And then finally, we are going to determine the arc rate value by using the steam table. The one that you got from a table is going to be the most accurate because those values are from experiments. Okay, then we can calculate the error between the ideal gas equation and the compressibility chart to see how much error is involved by using those equations. So that's our plan. So let's use the ideal gas equation first. How can we use this ideal gas equation? Ideal gas equation, PV is RT. And we want to determine this specific volume. And then what is the pressure of the system? 16 megapascal. Here, 16 megapascal. So I'm going to write 16? No, 16,000 kilopascal. Then what about this gas constant? Gas constant can be determined by this equation. Universal gas constant R bar divided by molecular weight, capital M. This capital M is not mass, molecular weight, not mass. Mass is lowercase, capital is molecular weight. And this molecular weight can be found from table A1. And this gas constant R is going to be always 8.314 kilojoule per kilogram Kelvin. Then what about this molecular weight? We can find it from table A1. So let's go to table A1. In this table A1, there's water and M is right here. The molecular weight of water is going to be 18.02. 18.02. What is the unit of this molecular weight? Kilogram per kilomole. Kilogram per kilomole. Oh, I made a mistake here. So this R has a unit, kilomole. Then you can cross kilomole, kilomole, then you get the gas constant of water. What is the gas constant of water? Let me do the calculation. Calculator. 8.314 divided by 18.02. We get 0.461. 0.461 kilojoule per kilogram Kelvin. Then what about temperature of the system? There's a temperature 360. So you are going to write 360 degrees Celsius here. Then you can determine the specific volume. Am I right or there's a mistake? Yeah, one mistake. Kelvin, right? So you have to add 273. Okay, I'm going to add a few stars to show that how important it is, right? 3 stars. Use Kelvin, okay? Then you can determine the specific volume. If you do, you will get approximately 0.0183 cubic meters per kilogram. So that's what you got by using the ideal gas equation. Now, let's use the modified ideal gas equation with compressibility factor Z. And the equation looks like this. PV is ZRT. Then the question is how to evaluate this Z. We can use reduced pressure and reduced temperature. Reduced pressure first can be determined by pressure divided by critical pressure, and reduced temperature can be determined by temperature divided by critical temperature. Then what is the pressure of our system? 16 megapascal. So this one is 16 megapascal. And what is the critical pressure? Where do we get this critical pressure and critical temperature? From table A1. A1. So let's go to table A1. So critical pressure is going to be 220.9. However, the unit is bar. So it is 22.09 megapascal because 1 bar is 100 kilopascal or 0.1 megapascal. So this one is going to be 22.09 megapascal. A1. Yeah, A1. This one A1. A4 is, just for your information, superheated vapor table for water. And we have temperature of our system 360 degrees Celsius divided by the critical temperature is going to be 647.3. Of course, this is incorrect because when you use this temperature for reduced temperature, use Kelvin. So 360 plus 273. Kelvin, Kelvin. So what is reduced pressure? 16 divided by 22.09, we get 0.72. 0.72. What about this one? 0.89. And we are ready to find Z value. So let's do that. Reduce the pressure first. It is 0.72. Where is the reduced pressure on this graph? The horizontal axis is reduced pressure. So let's find 0.72. It is somewhere here, right? So 0.72 is somewhere here. That is 0.72. And what is reduced temperature? 0.98, slightly below this line. So each line represents a specific reduced temperature. So this one is reduced temperature 2. This line represents 0.5. This line represents 1.3. This line represents 1.2, 1.1. This one is 1. So where is 0.98? Right below. So let's find the value. So 0.72. So somewhere here. So what is the Z value? Approximately, I think 0.67. So from this compressibility factor, we can determine the compressibility. From this compressibility part, we can determine the factor, 0.67. So I'm going to use this 0.67 in this modified ideal gas equation. 0.67. R is this one, 0.461. Temperature is this one, 633. And pressure is 16,000. Then what is the specific volume? We get approximately 0.0128 cubic meters per kilogram. Then the last one, by using the steam table. So we have superheated vapor and pressure is 16 megapascal, temperature is 360 degrees Celsius. So what is the specific volume? Right here. 16 megapascal, 360 degrees Celsius. Specific volume is this number, 0.011. So by using steam table, which is the most accurate one, 0.011 cubic meters per kilogram. Then what is the error between this one and this one and this one and this one? A4, superheat vapor, table A4. Then how can you determine the error? By using this equation. For this one, 0.0183 minus the reference number, this one, 0.011 divided by the reference number, 0.011. That's how you get the error. Zero 0.0183 minus 0.011 divided by 0.011, we get 0.66. What? I'm sorry, 0.66. Yeah, that's correct. So 0.66, which means 66%. And is this in an accepted range? Of course not. That's too much, right? That's why you cannot use the ideal gas equation for water. Then what about this compressibility factor? If we use this one, what is the error? 0.012 minus the reference number, 0.011 divided by 0.011. We get 0.09. So what is the percentage? 9% error. Okay, we have reduced the error significantly from 66% down to 9%, but still 9% is quite high. So you never use the ideal gas equation or modified ideal gas equation for water. Okay, but you can use for other gases, not just water. So any question about how to use the compressibility chart? No, that's it. So one more part. We're going to finish this one as fast as we can, then we can, discuss your first exam a little bit so that you can prepare for the exam. So moving boundary work. To understand this moving boundary work, let's come up with an energy balance equation. The energy balance equation that we studied in chapter 2 is heat transfer Q that goes into a system plus energy transfer by work that goes into a system minus energy transfer comes out of the system, either heat by work is going to be the total energy at the final state minus the total energy at the initial state. So what that is, mass times total energy per unit mass, U2 plus kinetic energy, velocity 2 square over 2 plus gravity times elevation Z2 minus mass times U1 plus velocity 1 square over 2, that is the kinetic energy and potential energy. From this, we usually neglect kinetic energy change and potential energy change, so you can cross them out. Then what do you have? The right-hand side, we have mass times U2 minus U1. So the internal energy change of the system. So this equation, the left-hand side shows energy transfer either by heat or work. And what is the right-hand side? The change of energy. So the left-hand side is the cause, the right-hand side is the result, which means, think about this way. You go to a bank and deposit $10,000. So $10,000 goes into your account, that's energy transfer. And your balance goes up by 10,000, that's the energy change. When we throw, the 5,000, minus 5,000 is the energy transfer, and because of that, the balance change is going to be minus 5,000. So the left-hand side, the right-hand side, they mean two different things. You go to, the buffet, the dining hall, and it's, maybe how many? 10 hamburgers. That's energy transfer. Because of that, you gained 200 pounds on the day. That's the change of energy. Two different things, cause and because of that, this is a result, right? Makes sense? Then let's think about the two examples. I'm going to give you two examples. And one thing that we cannot explain by using this energy balance equation. The first one is I have a rigid container. What does rigid container means? Volume is constant. V1 is the same as V2. So initially it has 20 degrees Celsius air. And now I'm going to, prepare another container, but this time it looks like a piston cylinder device. It has 20 degrees Celsius air, 1 atmospheric pressure, 1 atmospheric pressure. Are they the same system or not? Are they same or not in terms of the system? Yes. Wait, they look different. One is rigid container, the other one is piston cylinder device. Are they different? Then the question is, what is your system here? Rigid container? Is that your system? Piston cylinder device? Is that your system? What is your system? The air is inside the system. So the temperature of air is 20, pressure of air is 1 atm, temperature of air 20, pressure of air is 1 atm. Are they the same system or not? They're the same. Now I'm going to increase the temperature. So providing what? Heat transfer. So there's a heat transfer goes in. So I'm going to heat the system to raise the temperature up to 90 degrees Celsius. Good temperature to brew coffee, right? So I'm going to increase the temperature. So there's a energy transfer goes in, Q in. So eventually it becomes 20 degrees Celsius. I'm sorry, 90 degrees Celsius air. And I'm going to heat this system too to increase the temperature up to 90. So now we have air at 90 degrees Celsius. What happened to the piston? It stays there. If you heat it, what happens? It goes up or down? It goes up because air expands, right? When you heat air, it expands, right? That's how we, the first flight long time ago, hit the air inside this balloon. And then, it becomes lighter because it expands. So we go up there and never come down. No, we want to safely come down, right? So the piston moves upward from here, originally here, and it moves upward. And now it is up there. So this is the air in the system. This is the air in the system. Let's talk about our system in terms of the total energy. The total energy of air in this rigid container, the total energy of air in this piston cylinder device, are they the same or not? Not anymore. Why is that? Because of the volume extension, right? So if you look at the right-hand side, the right-hand side shows the change of energy. So this U1 represents 20 degrees Celsius. This U2 represents 90 degrees Celsius. So in this right-hand side, can it explain the difference in the total energy between here and there? It can't. Why? Because of the expansion. And if it expands, there should be work is involved, right? Without work, there's no expansion or compression. If you have this water bottle, if you want to compress it, you need to provide work, right? So there should be work involved in this expansion, but the right-hand side, the change of energy cannot explain that. Now that's a problem. Now, our energy balance equation is incomplete. So let's make it complete. Let's complete it. How can we do that? We know the cause of this volume expansion is work. So can you quantify the work? What is the work here? What kind of work? Can you determine the work? You can. Heat? Oh, no. Heat is used to increase the temperature from 20 to 90. So this is the energy due to the heat. Then what kind of energy, what kind of work changes the volume? Is it electric work? Mechanical work, right. So how many mechanical works did we study in the previous chapter? Kinetic energy, potential energy, 2 of them? One more, 3. What was the last one? Flow energy. What is flow energy? Pressure times volume. Do you remember about the story that I told you that I was too famous? There were 500 students. There's one more student want to come in. So if the one more student wants to come in, what he need to do? What she need to do? Push someone. Providing pressure. And then make my space. Then walk in, right? Pressure times the space, volume. Pressure times volume is the work associated with that. So this much volume is the result of pressure times volume. Pressure times volume. But you cannot just say pressure times volume. If it is constant pressure, and you can say pressure times volume, but pressure can change, volume can change. So mathematically, it should be integral of pressure over volume from the initial state to the final state. This is work. And this work is different from W in or W out. So I'm going to say this is moving boundary work. This B stands for boundary. So because of this energy transfer boundary, which is this piston moved. So there's a work associated with this boundary movement, that is moving boundary work. Moving boundary work. Oops. Whiteboard care. Oh, that was too much. Oh. So that is moving boundary work. Now, this moving boundary work, WB, should it be W in or W out? Out. Why is that? Because this one is pushing the surroundings, right? So when there is an expansion, that's the work provided by the system to the surroundings. If there's a compression, it is the work done by the surrounding on the system. So that's the direction. The direction of energy transfer is extremely important. When there's an expansion, moving boundary work WB is going to be positive. When there's a so that's W out. When there is a compression, it's going to be W in. Then this equation should be rewritten to include this WB. Make sense? Okay, so I'm going to do that. So there's WB. I'm going to include WB here. So instead of this energy balance equation, this time we have Q in plus W in minus Q out minus W out. Now WB, but WB may not be the only W out. There can be additional W out. So I'm going to say minus W out, everything but B. Make sense? So W out has this one, is going to be mass times U2 minus U1. Now there's another problem. Okay, so now we included this WB. So after this heating process, there was a moving boundary work. So is it energy transfer or the change of energy of a system? That work is given. So is it a part of the total energy or not? Still energy transfer. Is this movement, is it still the energy transfer or the change of energy? Change of energy, because the volume expanded. Not going to go back. That's going to be another process. After this expansion process, this is the total volume. This is the total energy. So this WB should be the change of energy. It cannot be here. It needs to go to the other side. So let's move this one to the right-hand side. Now, the energy balance equation is Q in plus W in minus Q out minus W out. Everything but moving boundary work B is mass times U2 minus U1 plus moving boundary work. Now, is that right? Yes, this is right. This is the final version of energy balance equation for closed system. But there's one thing that bothers me. This subscript is just too long, right? I'm going to. So we know that this W out is energy transfer by work done by the system to the surroundings, except moving boundary work. Then this is the energy balance equation for closed system. So this is the energy balance equation we are going to use whenever you have a closed system, which is this chapter 3. Now, let's see, can we solve this equation or not? How do you answer that? Do you know at each term one by one? If you know each term one by one, then you can solve it, right? So let's look at this Q first. Do you know this Q? Yes, heat transfer. When do you study? Next year, next spring. So IET356, right? So until then, let's assume that we know that, okay? This energy transfer by work, did we study? Yes, in chapter 2. You remember the electrical work? Voltage times current times delta T. Yes. So we know them. And do you know U2 and U1? Yes. We studied the table problem. Now you can determine, you can evaluate U, the specific internal energy of your system. The previous table problem in this chapter was for enthalpy, H. You just need to replace this H with U or V. Now the problem is that we do not know this WB yet. So if you know how to evaluate this WB, then you can analyze a thermodynamic system. By the way, I'm the one teaching IET356, but I won't be here next semester because I will be gone for sabbatical. I don't know who is going to teach that. If you want to see me, you need to wait another year, right? Because it's going to be offered only in spring. So I guess that, that this is the last semester you see me. So let's find, how to evaluate this WB. Then, is there any equation that we studied how to evaluate this WB? Yes, there is. I show you, this is the equation, WB, integral P over volume from the initial state to the final state. So that's how we evaluate WB. WB, moving boundary work, can be evaluated by this integration from 1 to 2 pressure over volume. Now, do you like this mathematics? No, that's okay, because we have a genius out there in the pure soul, those who majoring mathematics, solved this equation for us. So let's review their solution. Telling you nothing is difficult in thermodynamics. It's pretty simple and straightforward. You just need to focus on my summary. So let's study this moving boundary work. So we are going to learn how to evaluate this moving boundary work. So what is the easiest way to to evaluate this moving boundary work? Any random system, any random process? No, it's going to be complicated. So let's study some simple process. I'm going to go with the simplest one. Number one, constant volume process. When you have constant volume process, what is the moving boundary work? You can answer that without even looking at that. What is the moving boundary work when you have a constant volume process? Zero, because it's a constant volume. Is there a moving boundary? No. So the moving boundary work when you have a constant volume process is zero. Very simple. Number two, then another constant process, constant pressure process. Can you solve this equation? WB is integral pressure over volume from the initial state number 1 to the final state number 2. Yes, you can. Let's go over together. So pressure, is it variable or constant? It's a constant pressure process. So if we assume that it's a constant pressure process, is it variable or constant? So if you have a constant, what do you want to do? Yeah, you kick it out of this integration, right? So pressure comes out. And now we have integral dV from 1 to 2. Do you know how to solve this one? Now, yes. If you don't, let me write it here for you. Integral from 1 to 2 dx is going to be x2 minus x1. So what is integral dv? v2 minus v1, right? Pressure times this one, x2 minus x1 dx, dv, v2 minus v1. So in this v2 minus v1, what is v1? the initial volume, what is V2, a final volume, then what is this P? Is this P P1 or P2? It's a constant, so P1 is P2. So if you see there is no subscript, then you can say P is constant, so you can put P1, P2, doesn't matter. Number 3, constant temperature process. So now, can you solve this equation? The question is, what is the relation between P and V? We need to know the relation between P and V to solve this equation. So is there any equation that you studied that has the relation, that shows the relation between P and V? Is, in other words, has there any equation that you studied has pressure volume together? Yes, PV is MRT, the ideal gas equation. So let's talk about ideal gas equation. You can say PV is RT, but we have a capital V, so you can say PV is MRT. Yeah, this is the equation has a P and V. So let's talk about that. Is this P variable or constant? Variable. It's not constant pressure process anymore, so it's a variable. What about this volume, variable or constant? Variable. What about this mass, variable or constant? It's a closed system. So what is the definition of a closed system? Completely closed? No, that's not the definition. The definition of a closed system is mass is constant. When there's no mass change, it's a closed system. So mass is constant. Is the what is R? Gas constant. So is this gas constant? Variable or constant? That's the stupidest question, right? Because the name is constant. So R is constant. What about this T? Constant or variable? Constant or variable? Constant. So if you look at this one, the right-hand side is constant. That means pressure times volume is constant. Pressure times volume is constant. What does it mean? Whenever you have a gas at the same temperature, if you change pressure, if you change the volume, you can have various pressure, various temperature, but if you calculate pressure times volume, should be always the same number. So initial pressure times initial volume should be the same as final pressure times final volume, or if there's a more state, like a P3, V3 should be the same, P4, V4 should be the same, P2 million, V2 million should be the same. The point is, whenever you have a constant temperature process, pressure times volume should be the same number. So if you increase pressure, volume will decrease to meet the same number, PV constant. So there is a relation. So can you replace this P with V? Yes, we can. So PV is constant. In other words, P is C divided by volume. Because if you divide by volume in each side, P is C over V, right? This one. Now you can replace, I don't like this P, so let's replace this P with V. Yeah, we can do that. So this one becomes integral C here, dV over V from 1 to 2. Then what do you want to do? Oh, there's a C. What is it? Constant. If you have a constant in this integration, what do you want to do? Yeah, going to go outside. So there's a C in front. Now, integral dV over V. Do you know how to solve this one? integral dx over x from 1 to 2 is going to be natural log ln x. You remember that? 2 minus ln x1, which is ln x2 minus over x1. So similarly, the solution to this dv over v, integration of this dv over v is going to be natural log v2 over v1. Wait, what about this C? Oh, C is here. C is pressure times volume. So I'm going to say this C is pressure times volume times this one is natural log V2 over V1, natural log V2 over V1. V1 is the initial volume, V2 is the final volume. Then what about this PV? Is it P1 V1 or P2 V2? Doesn't matter, because P1 V1 is the same as P2 V2. But you cannot say P1 V2 or P2 V1. Only P1 V1 or P2 V2. So that's how you determine the moving boundary work for constant temperature process. And the relation that we use is this one. PV is constant. Any question up to here? So finding, the moving boundary work is not difficult as long as we have a constant volume, constant pressure, and constant temperature. But not every process is one of these three. What about volume changes and pressure changes and temperature changes? The real gas behavior is called polytropic process. In this polytropic process, we say PV to the power n is constant. What does it mean? When there is a random process, when you measure pressure and the volume at different states, it turns out, it follows this rule. Then what is this n? This n is polytropic exponent. And how do you get this n? There's no table for that. There's no equation for that. You run an experiment to determine this n. So then that n is going to be case by case. So if this is the case, then how can you determine this WB? No problem. We can solve the same equation. WB is integral 1 to 2 PdV. Then the problem is that we need to know the relation between P and V so that we can replace this P with V. Then you can solve that integration. Then what is the relation? It's right here. PV to the power n is constant. Then you can divide each term by V to the power n. Then what do you get? P is C times V to the power 1 minus n. If you divide each term by V to the power n, V to the power n, 1 over V to the power n is V to the power minus n, right? Then this equation becomes integral 1 to 2 C V to the power 1 minus n dV. Then C comes out. Then how do you solve the integral of V to the power n? Integral x to the power n dx is going to be 1 over 1 plus n x to the power 1 plus n dx. So that's how you solve it. Then the same thing. v to the minus n is going to be plus 1. By the way, c comes out, c times 1 over 1 plus n, no, there's a minus n, 1 minus n times v to the power 1 minus n, this is the final volume, minus v1 to the power 1 minus n. So this is it. Then what is this c? This c is pv to the power n. So this equation becomes pv to the power n over 1 minus n times v2 to the power 1 minus n minus v1 to the power 1 minus n. Then this pv can be p1 v1 to the power n or p2 v to the power n. So let's go to the left-hand side. So it's going to be pv to the power n times v to the power 1 minus n. Wow. pv to the power n times v1 to the power 1 minus n divided by 1 minus n. Then this one, you can say p2 v2, p1 v1. Then, now, this one, this one, this one, this one, we can cancel them out. Then what do we have? WB is P2 V2 minus P1 V1 over 1 minus N. That wasn't easy, right? But do you need to understand the procedure? You don't have to. You just need to, write them down on your formula sheet and then use it when you solve, when you determine any moving boundary work. What? You don't have to go through that. I just show you, how we got these equations. But it's pretty simple. We just solve this one. The clues are over there. You can practice. It's a good time to practice mathematics, right? Then that was too much mathematics. I agree with them. So let's find another way to evaluate this moving boundary work. Is there any other way other than this mathematics? Yes. I can use a graph. So we are, calculating this one. Can you solve this one on a graph? Yes, you can. What is this integration means on a PV diagram? Let's say there's a number 1, initial state. This is number 2, the final state. I don't know how they are connected. Maybe this way, this way, this way. Then integration means, what is the integration of point? Line. What is the integration of line? The area. What is the integration of area? Volume. What is the integration of volume? I don't know. So this one is the line. That is PDV. So if you determine the area, that is WB. The question is, how are you going to calculate the area? There's one way you can do. If this line is straight, then you can determine the area, right? This one, PV graph. There's no specific name, okay? So there are 5 different ways to evaluate this moving boundary work. And one last thing. This moving boundary work can be positive and can be negative. What does it mean when it is a positive value? And what does it mean when it is a negative value? It is related to the moving boundary. What is the result of moving boundary? Either expansion or compression. So plus minus should be related to expansion or compression. So you have a 50% chance. So it's going to be either this one compression or expansion or the other way, right? So positive moving boundary work, expansion or compression. You win, expansion. So there's a 50% chance. So what about this one? Now you have a 100% chance. Negative moving boundary work means compression. So this one is compression. This one is expansion. Then when you calculate this area, is it a positive value or a negative value? Can an area a negative value? Maybe in Interstellar or some movie, right? But in reality, no. The area is always a positive value. Then, if you calculate the area to determine this WB, once you get the area, is the end of finding this WB? No, you need to determine the sign of this WB based on whether it is an expansion or compression. You don't have to do that if you use this equation. If it is compression, you will get a negative value. But if you use this graph, you need to determine the sign, okay? So that's everything about moving boundary work. Write them down on your formula sheet. So based on that, I have two problems, but I want to solve all of them. Let's solve the one easy one, just to get the idea how to determine this moving boundary work. And then, we will stop there and then, discuss the exam. Calculate the total work. So that's going to be moving boundary work, unless, it shows that electrical work or shaft work or spring work, there's no information. So the only work you can calculate is going to be moving boundary work. And there are many different ways to determine this moving boundary work, not many, just 5, but we have a clue here. It is an isothermal process, that means constant temperature process. So what is the moving boundary work here? So WB is PV natural log V2 over V1. So if you solve this one, you get the moving boundary work. So let's see. At the initial state, number 1, initial state, what is the pressure? P1, 200 kilopascal. What is the volume? It's not given. What about the final state, number 2, P2? The pressure, 600 kilopascal. What about specific volume? V2 is 0.2 cubic meters per kilogram. Now, let's look at this one. Do we know V1 or V2? None of them, because these are actual volume. This one is on a specific volume, but we know the mass of the system, 3 kilograms, so you can determine actual volume V2. So this V2 can be determined by mass times specific volume at the final state. Then mass is going to be 3 kilograms, and the specific volume is 0.2 cubic meters per kilogram. Then the final volume is going to be 0.6 cubic meters. Okay, we have that. Then what about V1? Can we determine V1? If we have a constant temperature process, we can use this pressure volume relation. PV is constant. Writing in here, PV is constant, meaning P1 V1 is the same as P2 V2 is the same as P3 V3 P 2 million, V 2 million. You remember that, right? So we can use this equation. What is P1? 200 kilopascal. What is P2? 600 kilopascal. What is V2? 0.6 cubic meters. What is V1? 1.8. 1.8 cubic meters. Then what about PV? We can say P1 V1 or P2 V2. Let's say P1 V1. Then what is P1? 200. What is V1? 1.8 cubic meters. So if you do the calculation, you get WB 3,395.5 and negative kilojoule. So this is the moving boundary work. Why there's a negative sign? Why there's a negative sign? Because why there is a negative sign? Because it is a compression process. And let's check whether it is compression process or not. Initial volume this much, and final volume is down to this much. So there was a compression. Any question about this problem? No? That's all for today. We have 10 minutes. So let me go over. Let me, discuss what's going to be in the first exam. Ending the recording.